Great. Good morning, everybody. Good afternoon or evening, wherever you are. We'd like to welcome you to our webinar today, Training Your LLMs with Classification and Regression Tasks. My name is Morgan Mills, and I'm on the marketing team here at H2O. And I'd like to go over a few logistics before we get started. We have launched a poll. Quite a few of you have already answered. If you have not, please go ahead and submit it before we get started. There is a chat box that you will see for Q&A. If you would please feel free to send us your questions throughout the session. Rob will be answering questions throughout his presentation, and we'll also have a few minutes at the end for more questions. This webinar is being recorded, and we will be sending out a copy of the recording via email later this afternoon. So thank you again for joining us. And without further ado, I'll hand it over to Rob Mulla.
Thanks, Morgan. All right, so we're off. We're going to be talking about classification and regression with LLMs. I put regression here in parentheses because the focus is mainly going to be on classification tasks. But this is a really cool topic that I haven't heard talked about too much, and actually came out of some research that was done by the H2O team. Not that they were the first ones to do it, but the H2O GMs competing in some Kaggle competitions were really able to leverage LLMs for tasks that you don't necessarily commonly see them used for. And we're going to go over not only how this works, we're going to go over some background on how LLMs work so we can kind of understand how we apply it to these classification tasks. We're actually going to show you how you can do this yourself really easily using H2O's open source LLM Studio. And then we're actually going to jump into some code. If we have time, I've reserved some time here at the end to code up actually running the inference and exploring how these models are a little bit different. As Morgan mentioned, there's this poll. So if you haven't answered the poll yet, the question is, have you ever fine-tuned an LLM? And I could see that we do have maybe 17 or 20% people have, but most of you all have not fine-tuned a large language model, which is absolutely fine. You're in the right place then. And out of those people who haven't fine-tuned an LLM model, most of you want to. So you're definitely in the right place if that's you, and hopefully for everyone else also. So I'll very briefly go over some background about me. I am a principal data scientist at H2O. I've worked in various industries, doing various different things, working specifically with data. And I've studied at schools, and I also, last little thing, have do stream from time to time and create videos and other content on data science and machine learning. So if you enjoy what you hear today, you can also follow me on any of those platforms. And in addition to that, I'm very active on the website Kaggle. I really enjoy competing there and learning as I try to solve problems on Kaggle. And really that's where a lot of the research, like what we're going to learn about today, has come out of. All right, so LLMs for classification, we're going to go through it like this. We're going to talk about LLMs from the inside out, kind of understanding how they work before we actually understand how we can apply them to classification tasks. Then some basics about fine tuning, since that's what we're going to be doing to create these models that can do classification tasks, and talk about a little bit about quantization because that's built into LLM Studio. And then we're going to jump into fun stuff, at least what I think is actually doing some stuff and actually seeing how we can train these models. So feel free to ask questions as we're going along here into the Q&A. I know someone's already asked if we're going to have these slides public afterwards. We are going to upload this whole video online. So, All right, so what's actually inside an LLM? I'm assuming many of you have already interacted in some way with a LLM, either be an open source LLM like Llama, which I'm showing here as an example. The Llama 2 models are some of the most popular open source large language models that are out there nowadays. Not only open source, but open weights, meaning that you can download these weights from this model and use it and interact with it. But what's actually going on under the hood? So Llama Llama 2 has come out in a few different sizes, the 7 billion, 13 billion, 70 billion parameter model. And that kind of gets at one of the two aspects that I want to talk about when we understand or trying to understand what a large language model is. And the first one is basically the architecture of the model. And you could think about this as just a graph representation of a bunch of matrix or math multiplication that's occurring within the model in order to get our solution. So I actually am linking here, and you can put this in your browser too, this link, this bbycroft.net/LLM, because it's a really cool website that I found. Someone showed me that helps us understand what these models look like underneath the hood. And in all these open weights models, you actually know how this model structure looks. On this website, you can actually take a look at GPT-2, Nano GPT, GPT-2 XL, and GPT-3. But I want to focus in on Nano GPT because you can actually see here all the different matrices of numbers that are used to be multiplied or added together in order to create our output. Okay, so it sounds pretty simple, but the main thing to understand is we know what the structure looks like and we have a good understanding of how the math works. But actually, the fact that it's able to predict and produce an output is dependent on a second part, which is the model weights. So this is the actual values within this LLM, the weights values in each of these matrices. And these are values that are learned by a process called training this model. So hopefully you guys understand that process. And usually that's done in two different steps. And we're going to talk about those two different steps. So training the weights really instills the knowledge about the model. So usually this training is done in two different steps. A pre-training stage where we have a large amount of data that we train the model on, and it requires a heavy amount of compute. We're talking about thousands of GPUs, and it's very expensive and time intense. Takes weeks, even months to train these types of models. But all it's really trained on is a large portion of the internet, and it's trained to predict the next token for whatever we're given. So this is a process that we don't necessarily want to do often, but it's awesome that we have open source models like Llama that we can use that already have been pre-trained on this large amount of data, and we can leverage that. All right, so for a simple example, once we have this base model that has been trained on a large amount of data, we can give it an input and it's going to predict for us the best output or the most likely output that it thinks based on that input data. However, this model hasn't been trained to do any specific task. It's just been trained to predict the most likely output. So for instance, if we gave this base model the input of 10%, and I specifically chose a very vague input to the model. And I'm providing this to the Llama 2 7 billion parameter model. The output from this model is actually just going to be taking that input and running with it, predicting what it thinks is the most likely next token based on that input. So this is kind of funny, but also we're going to do this in the code later, but it shows how the output of just putting in 10%, I guess I put 15% in when I typed this initially, but it's running with it and saying 15% off 500 plus vintage watches at Watch Finder. The 2017 watch fair is a celebration of the very best watches. And there is some randomness in this, so it's not always going to produce this output, but it's kind of just blurting out the text that it thinks might follow this input 10% value that we gave it, the token of 10%. And it's very important to understand that these base models on their own are essentially just taking these terabytes of data of the internet and compressing them into those weights that we looked at before in order to produce a prediction of what the next value in a sequence of sentences would be. So that on its own isn't necessarily very helpful for us. And this output, we also aren't entirely sure if what it's giving us is just random or if it's actually somewhat rooted in truth. And there can be a lot of hallucinations and just text that sounds like it makes sense, but it isn't necessarily what we want. So these base LLM models are great because they have that foundation compressed information from the internet. It's all instilled in these model weights, and it's able to sort of predict what it thinks should come next. But these foundation models have very little direction. They don't know exactly what they're trying to predict. I like to think of it as basically they'll vomit out the internet at you when you prompt it with a question. So how do we make this useful? Well, we do this in the second stage of training, which is called fine tuning. So we talked about before the pre-training, large data, medium to low quality text requires a lot of compute and not something that you want to do often. Now, the next step is taking these and actually fine tuning this on high quality data. Now, this data is in much smaller of a size, or it doesn't need to be as large as the terabytes or tens or 20s terabytes that we would train the foundation model on. But it's more important that this data and these question answer prompts are very high quality. So we want them to be actually in the format that we want the output of the model to look like. So nice thing about this is there's a lot less compute required. You don't necessarily need those thousands of GPUs to train, and you can train these type of models in hours or days or even minutes, depending on how small your data is. So I see that an attending was asking 10% of what? It looks like it is depending on how you make your query. So that's a great question. So this question this prompt that I gave the base LLM of 10% was purposefully vague because I wanted to see what the output would be from the base model. And it kind of leads into this next slide where I actually show what the output of a fine-tuned Llama 2 7 billion parameter chat model looks like. So if you go into H2O GPT, the public version that we have, and you typed in 10%, the Llama 7 billion parameter would instead, the chat version, and this is a model that has been fine-tuned to be a chat assistant, would respond with 10% is a fraction decimal and percentage that represents the value out of every 10 equal parts. And then it continues on, and I even had to cut it off because it went down and explained it. But you can see that there's formatting involved with this. It knows to hit various points of what 10% is. And even with the vague prompt of just asking it 10%, it knows the most likely answer once fine-tuned is to be a helpful assistant that explains what 10% is back to us. And then you can imagine how when our questions are more complicated, it's better. And you all have probably experienced this interacting with LLMs that are out there. So the next question is, all right, how do we actually, and this is a little bit more of a technical part, but how do we actually train and fine tune this model when we have our quality data that we want to be representative of the actual question answer pair from our fine tuned data set? Now we could go in and take all these billions of parameters that have already been trained on the foundational data and try to train them on the additional high quality data. But the thing is, that's like trying to move a tanker ship. We've already instilled all this information into that model, and those weights contain valuable information that we don't necessarily want to change or modify. We just want to change how the model responds and the type of voice that it responds. Another thing about this is if we did train all those weights, we would require a large amount of compute because that's a large amount of the more parameters we need to tune, the more training epochs and data is required to actually get a quality change in the model. So out of this came some great research into something called LoRa, which stands for low rank adaptation. And essentially what we're doing when we train using LoRa is we take these existing foundational weights and we freeze them. We tell the model training process not to change any of those weights that have learned that foundational information, but instead we have a lower ranked representation of these that are running almost in parallel to these pre-trained weights, but on a much smaller scale. And then we train these alongside. And actually doing this allows us to train much quicker to get a model that responds in the way we want trained on a much smaller number of documents, and has really been proven to create some really good results. So all of that's to say, if you don't care about the technical nitty gritty of LoRa, what's going on is that we're tweaking the model to produce an output that we're hoping to find while keeping its knowledge intact. So I think this cartoon kind of gets at the essence of what we're doing. We're kind of sticking LoRa onto the side of the model and training that so that when it combines with the knowledge of the model, we produce an outcome that is closer to what we're trying to get the model to respond with, not just that sort of vomiting of the internet back at us. Is there a difference between chat? Okay, so now I'm looking at a few of the questions, one from an anonymous attendee. Do we need 1,000 GPUs if we want to pre-train on specialized data that is way smaller? No, we don't. We can use LoRa on top of these pre-trained weights. And remember, this is the real benefit of having these open weights models, is that we can train now on top of them using LoRa. This is very similar to what has been done for many years with image classifications. Much of the time, these types of models are already trained on a bunch of images to start with, and then we kind of use transfer learning to as a starting point when we want to train those image models on a specific task. Here we have a general model, has a good understanding of the internet and has that data instilled in it, and we're fine tuning it to do a specific task. All right, so these next few slides might seem like a side note, but it's important to know, I think, because it's built into a lot of the fine tuning processes, but it's the idea of quantization. So one of the big questions that we get when talking about these models is how much memory or how big of a GPU do I need in order to train or in order to run inference on an LLM? And it's actually quite simple. We can just take this equation where we have some information we know about the model, and we can compute the amount of memory required in order to run it. Based on the parameters that the model has. So let's say we're talking about the 7 billion parameter llama model, that would be P, bytes used for each parameter. And then we're going to talk about this bottom part of the equation. But then over here on the right, just to add some overhead, because the model is not the only thing added onto the GPU when we are doing these computations, we add about a 20% overhead for the actual prompts to be loaded on there or anything else the GPU needs to use. So we can just compute based on the parameter size of our models. And these values in this table don't include this 20% overhead, but you can see with a 7 billion parameter model, you need 28 gigabytes of RAM, which is fairly large. And then once you get to these really large models that perform much better because they have more parameters to learn the internet, you actually start getting into the area where you don't have commercially available or graphics cards that are the size that you and I might be able to purchase that would be able to fit these models onto the memory. And I kind of glazed over this, but in order to run these inference or these computations, you really need a GPU or some sort of specific hardware that's able to run these computations, to run these model weights when you're running predictions. But so really cool research has come out that, and this isn't necessarily new, it's been used in deep learning for a while now, which is the idea of taking each of these values that our parameter represents. And by default, many parameters, many values are represented by bits, ones and zeros. And by reducing the number of bits that you're using for each of the parameters or the number of precision, basically what you're doing is reducing the quality of each of those individual parameters. So if we go back into this visualization, if we take how many values are actually possible within each of these dots in this model, and we reduce it, we can actually cut in half or into a quarter the amount of memory that we need to use in order to run these models. And what people have found is even by taking these large language models that were trained that are billions of parameters and cutting down the precision of each of these parameters that's used, you can still get pretty good results and require a lot less memory to use. So now we can see that if we're using, instead of float 16, we're using integer 4s, we've gone all the way for the 7 billion parameter model of requiring 28 gigabytes of memory down to only 3.5. And this is well below the size needed to fit these models on a single GPU. Not only that, but quantization can be combined with LoRa that we talked about earlier, to actually speed up the time it takes to train the LoRa portion of these models. So these are kind of the two big things to know about, LoRa for fine tuning, and then the quantization that we can do in order to really, this little trick to speed up our processing time, our memory requirements, and our inference time. So you might be asking, okay, there's no free lunch, right? You can't just make the precision less and not degrade in quality. And that's true. And there are a bunch of different benchmarks out there to compare how these models perform in their full precision versus quantized version. And actually what we find is that for the most part, quality isn't degraded linearly, or it isn't degraded as much as you would think for for each reduction in size. There's definitely a noticeable difference, but in many ways, in many situations, this is more important to reduce the size or the quality using quantization than it is to use these models at full precision. Let me look a little bit at these questions. There's a lot of detailed questions that probably I'll get into later if we have time, or we can follow up afterwards. But I'm going to continue on here, and you might be saying, okay, at this point, I haven't really talked about classification at all. And that's the point of this talk, is to talk about how we train these models for classification. I gave you this whole background so that you could see how this process works, and how that second stage of fine tuning is typically used to fine tune an assistant, like ChatGPT, or a fine-tuned chat version of Llama or Falcon, or whatever model might be out there. This has primarily been the focus of the fine-tuning stage. But really, there's nothing to stop us from tuning these LLMs to do more traditional classical supervised machine learning tasks like classification or regression. And actually what we found is training these models to do classification tasks gives you the benefit of the model having this instilled knowledge of the internet, and does really good job of then performing classification on new documents, and is able to be fine-tuned on a much smaller amount of data than you would normally take if you were training a model from scratch. So if we think about classification tasks that we want to apply LLMs to, you could think about anything containing documents or text, and any sort of either binary or multi-class target that you would want assigned to this data. And using LLM Studio, I'm going to show you how you can take this type of data, fine-tune a model like Llama 7 billion, and have a really good out-of-the-box result for detecting things like, what's the subject domain of this? What's the age of the author? What type of document is? All these sort of classification tasks, as long as you have some data to train it on, you can do now with the LLM sort of serving as this background foundation. All right, here's the surprise, actually. So what you may have not already realized is that these LLMs are actually already multi-class classification models. So the way that they work, if we go back to this visualization of the output of an example GPT model, you could see that the model outputs this last layer, which is actually a prediction of which token should come next in the document. So whatever the vocabulary size of the model is, it could be, for instance, Llama 2, 32,000 different tokens that it's choosing from. All the model is doing currently is a classification task of which is the most likely next token to predict. But if we want to predict something more specific, like is this document written by a human or an LLM? Is this document, what's the sentiment of this document? We can actually take this last layer and add a portion onto it that we will train with to make it specifically set to answer those types of questions. All right, so now I'm going to actually jump over and show you LLM Studio and how we would train model to do this classification task. The great thing about LLM Studio is everything we talked about, LoRa, quantization, a bunch of other tricks that are used for training large language models that that get into more. We would be here all day if I went into all the detail. They're pre-built into this package, and they're built by some of the best data scientists at doing this in the world. And it's completely free for you to use even today if you want to. So let's do a demo of this by showing you LLM Studio. Before I do that, I'll just show you LLM Studio GitHub. This is the LLM Studio GitHub. You can go ahead here and star this if you're interested in it. And to get this set up on your machine, you're going to need at least a GPU running CUDA, so an NVIDIA GPU. It could be on a local machine or it could be a cloud instance, but they do walk you through all the steps here on how to get set up, making sure that you have the driver set up correctly. For me, it only took a few minutes to get this set up, and it's actually been getting better and better as more people comment and raise issues if they run into it. So feel free to go to this GitHub and check it out. But once you start it up and run it on your machine, wherever it is, you have this graphical interface. I'm going to show mostly through the graphical interface, but you can also do this tuning with a command line option if you just prefer to write your code instead of clicking around like this. So everything starts with importing a data set. We would just select and upload a data set either from something local that we upload or AWS or even on Kaggle. And the only requirements of this is that it's either a CSV, Parquet, or zip file that's going to contain columns representing what we want our target to be. So in this case, it would be a classification problem. So we would have either a binary 1 or 0 or a number representing what class we would like what that example is, and then the text values or multiple columns with the text values that we're going to talk about. And I'm going to just show you this data set that I've created from the data that we used in a recent Kaggle hackathon that we launched for our Gen AI World conference that we held last month. The data here is actually just a comma separated value file with a bunch of prompts and answers from open source large language models. And the target is which model out of the 7 produced the response. So you could see here, after we've uploaded this data set, we can even scroll through, double check and make sure the data is how we would expect it to be. Some visualization here of the prompt and answer. And even we can see some statistics like the length of that data. I can also show you here in this notebook exactly what this data looks like. So I'm going to go ahead and make sure I shut down this one, start this one up. This is essentially the trained CSV that I've uploaded to LLM Studio. I can show you here if I run a head command on this. We have these question response columns and then the expected target. So whatever data you have, as long as it's in CSV shape format, you will be able to upload it to LLM Studio and train your model. So you can see here we have almost 4,000 examples, which is not that much. And I even did some exploratory data analysis here. So just looking at the response length of the training data, if I group by the target, so this is the type of model, we could see that the different types of models do produce different types, lengths on average in response. I even took one here of the example question that in this data set, and we could see print out what the response is based on the target. So target, this question is, how can I develop better problem solving skills? And the different models you could see produce very different types of response. Some have bullet points, others just answer right away. And what our model fine-tuning process is going to do is understand, or try its best to understand, the ways that these different models produce these responses, and create a new model to classify which model we're working with there. So, all right, so we have our data set created. Now all we have to do is create a new experiment, which you see here over on the left side. So when we click create an experiment, we can choose our data set, which is this, the detect the LLM data set I created before, essentially that CSV I just showed you. And in this drop-down menu, we just have to select causal classification modeling. And this will have all the settings in order to train this model to do classification. Pre-built into this, we can set the validation size. So this will hold out a portion of that training data set that it will run validation on every time that we run a new epoch, so we can see how well it's performing on unseen data. It's important to do this, especially if you have a good enough amount of data to run some sort of validation and actually see how your model's doing. Then we can have our prompt column, which I want to include both the question and the response. And our target, which is the actual model value, is going to be our answer column. There are some other parameters here for if there was some parent-child relationship between these different examples, but we're going to just ignore that. The next thing we need to look at here is the backbone data type. Now, if you notice here, we are using int for quantization for this backbone. Again, this is what we had talked about before, and how important quantization is to allowing us to train this model quickly and efficiently. And oh, I did also skip over it here, but we are using the Llama 7 billion parameter base model as the input to or as the main base weights that we're using. And then the one thing we need to also make sure that we select here, because we are doing a multi-class classification problem, is that we will select the number, not number of workers, the number of classes, there it is. From 1, we would set it to 7, since there's 7 different things we are having the model predict. And also, because we are doing multi-class, we would have to change this loss function from binary cross entropy loss, which would be just predicting between 0 and 1, to a cross entropy loss. And then we can just go ahead and run our experiment. Depending on how many GPUs you have running, you can let that go. So I did this just a few days ago, and I can see what my results are in this View Experiments tab. Now, this one example that did fail, just to show you, it failed because, oh, let's look at the logs, because I did give it this multi-class classification data set, and I didn't set the number of classes to 7. I forgot to do that. And the label was 1. So it gave me this error, but that was pretty simple to figure out. I just went back in and ran this one. It gives it a random name. This one happened to be Rainbow Corgi. And this is the results of the experiment. We can track the loss as it's going on. We can actually track the validation area under the curve as it's loading. And we can see the logs, many other things. One thing I want to note here is in the logs of this training process, I was able to train this on a single GPU in just about 25 minutes. So running validation took another 30 seconds, but this was very quick that I was able to quickly create a model that performs pretty well. And you can see the area on the curve is about 0.84 for this. There are some other built-in features that I won't go into, like the config file that you ran your experiment. You can export this and share it with other people running. You can also just double check to see on this holdout validation set, really quickly see how well it performed. So you can see here the target was 5, it predicted 5. Let's see if we found any that it got wrong. So here it did, even with the training, it got one of the labels incorrect, so it's far from perfect, but this sort of shows you how quickly this model gets to be very much in the realm of being usable for real-time applications. Okay, so now I know we all have about 15 minutes left, and I want to answer a few questions. I also wanted to just show you the example of once you've exported this model, how the output looks, and comparing this against that base model like I had talked about before. Let's see what people are asking though. Hi, can we take text from our data into the Q&A format required by LLM Studio? So how can we take the text from our data and put it into that format? So in the classification format, it's actually not going to be question answer pairs. It's going to be your text and whatever classification variable, either binary or multi-class as another column. H2O does provide tools for automating this that aren't necessarily open source, but part of working with H2O is your ability to have access to some of those sort of products. If you're just doing it on your own, it's something that you should be able to do with the smallish data set reasonably with something like pandas or even Excel if the data is small enough. Will this capability make its way into driverless AI? For now, this is its completely separate product than driverless, but these models can be deployed and used by something called H2O GPT-E, which is our enterprise H2O GPT offering. Any suggestions about hyperparameter tuning such as learning rate, LoRa-R? So one thing I will say about all these parameters that you have when you're tuning your experiment, so going back to create an experiment here, and let's change this to classification, is that many of these parameters can seem overwhelming, but the nice part is by default, they're selected to really be what normally works the best. As opposed to some other types of models that are smaller, really the configuration, the main parameters that affect how well your model performs is going to be the learning rate. And this is just going to be through experimentation, seeing how well it does. And then, of course, the number of epochs you want to train for, that will give the model more iterations through your training data when it's forming these weights for Laura. So these are two of the parameters that you can test with, modify, but really out of the box, you should get fairly good results. And I wouldn't necessarily recommend going beyond that unless you really see a need for that. And I'm sure if you post on the LLM Studio GitHub and ask them questions, they may have different answers or more recommendations on how to do that. Is there a possibility to test drive this H2O LLM Studio on a trial basis? So LLM Studio is completely open source and free to use now. I mentioned this at the beginning, but if you go to this GitHub repo, you can do everything that I'm showing you today out of the box. You don't need any license. It's all completely open source. You can, the best thing you can do is just star the repo and be thankful that we have this available to us. Maxwell says he has 2 questions that have been missed. I'll try to catch one of them. I have a really hard time constructing training data for fine-tuning an LLM, like the form and diversity of training examples is pretty perplexing. Will you be spending time on that? So we're not going to specifically be going over the data preparation today, but just to answer your question indirectly, what I will say is that training these LLMs for fine tuning for chat is much different than training for something like we're showing today with classification. And in a lot of cases, you'll be able to find these ground truth labels. They'll either be readily available to you. For instance, we knew exactly what the labels were to this data set when we created it, because we knew which models generated the output. Similarly, if you have a data set where you know the author names and you want to do a multi-class classification model, you will be able to, it's much easier to formulate that data set because the result is binary or multi-class as opposed to a text response, which could be in varying levels of quality. So that really is one reason why approaching some problems like this may be the best solution for what you're trying to achieve. Okay, so I do want to, this last little part is going to be a little bit more technical. So what I'm going to do here is actually show the code to load in this base llama model and then compare that to how our classification model works and see what the difference is between the actual architecture when we add this classification head onto the model. So if I go here and I load this base model, every model under the hood has this tokenizer, which essentially is taking your free text and converting it into numeric values, since the model needs to interact with binary representations of what we provide it. It doesn't understand what the text is. The model actually just understands the tokens that are created from the text. So I've loaded in this tokenizer in this base model. And just to show you how the tokenizer works, if I give it the text hello, you could see the input IDs. Well, let's ignore the mask for now, but the input IDs are actually the IDs of the tokens within the tokenizer. So if I take the tokenizer and I look at the vocabulary, these are all the different tokens that the model or that the tokenizer will take your text and split them into when before it feeds into the model. The important thing here is to be using the same tokenizer that the model was trained on when you do any sort of inference or additional training. So here we can see the length of this tokenizer is 32,000. That means there's 32,000 potential tokens that it will split your data into. And also notice that there are these underscores to represent spaces, and it may be that a token is just part of text. It doesn't necessarily need to be full words, but the tokenized text is just a chunked version of your raw text. So if I do something more long, thanks for attending this webinar where we are learning about LLMs. You can see that we have all these different tokens. And if I go maybe here, tokens, we take these tokens, and why don't I just go ahead and print each of these tokens? Or yeah, let's take, I'm just going to make this simple. We're going to take our tokenizer and convert these IDs to tokens. So we're take our tokens. So these are the actual values that are fed into the tokens that are fed into the model when it splits this input sentence, which is thanks for attending. All right, so the next is taking these tokens and actually feeding it into our model. You can see I'm setting our device. This is the GPU that is essential for running these types of models. And I'm loading this model onto our GPU. And then we're going to generate text from some input text. And before we use this example, 15%. So let's go ahead and run this. So this will take our input text, run it through a tokenizer, and then iteratively generate the next most likely token value from this input up to a max length of 150. And remember, this is the base model that hasn't been fine-tuned at all to do anything. And of course, like we saw before, it generates 15% off. I guess makes sense. 15% off when you just prompt it with 15%. Your next order with newsletter sign up at Fathead, whatever that is. So it's just generating. Remember, this is the vomiting of the internet type of model. Every time I run it, even it's going to say different things about 15% off on all orders. And it's clearly thinks that the word off is the most likely result from or token to occur next after 15%. Now, to look a little bit deeper into how this model works, like we had in this other visualization, we can see all the layers within the model, how they're interacting with each other to create the output. And then we can see here this LM head, which is the final layer that's predicting our next token, is predicting out of 32,000 features, which is the most likely. Those are the tokens that we were looking at earlier in the tokenizer. So if I just look at the raw output of 15% when we run this through our model, we could see the logits or the predictions for this input of 15% is of a shape of 1, which is the batch size, 4, which is the number of values, and then 32,000, which is the number of tokens. So it's actually predicting for each of those 32,000s, which it thinks is the most likely. We can run this argmax on it to get which token is the highest value for each of these 4 values. And if I convert these, we can see it says 19 off. So it's predicting this percent off as the next token. All right, but we trained our model specifically for classification. So now let's load in this same model, but with the LoRa fine-tuning done to it. And on top of that, we're going to add this new head portion of the model, which will then predict, instead of 30 out of 32 potential values, it'll predict out of 7 potential values what the output should be. So it needs to load this model. It'll take a few seconds. And we're just giving it this one example prompt of how are you? And we can see that these are the raw predictions coming out of the model for each of the 7 classes that we fine-tuned our model on when we ran it through LLM Studio. And the one that it predicts is simply the highest value out of all of these. So that should be here. So running argmax on this will give us the highest value. And it's predicted it as 5, which is this value, and it's indexed at 0. So 5 is actually the 6th value. Little bit technical, but I think it's important to see how this model can be used after it's been trained and how the architecture is slightly different, but it then allows you to achieve many things with doing classification tasks. The last thing I just want to show you is by taking this training data. So if we have our training data, that CSV that we had before, and feeding this back through that model that we've trained to see if it does it correctly. Now I'm running on the training data, which is, I guess you could say, a leak of information, but this will at least show us how the model performs, and that it is in fact predicting the right type of response. So I'm going to create a new column called prompt, and I'm going to use a combined representation of the question and answer. So now if I look at here, our prompt and our target, we can feed in one of these values and see if it gets the target correct with our model. So let's take our first prompt, which is this: explain the concept of coevolution, and then the text from the model's output. Let's make this our prompt. We can also print it. So it looks a little bit better with the printing formatting. And let's go ahead and run this through and see what it predicted. So it did in fact predict it was the 3rd model. And if we look here, that's the correct target for this. And ideally I would have done this on the test set, the holdout set, but I don't have the labels for that readily available. But I can, that might be a good offline thing for you to practice if you want to go through this and test out running LLM Studio to see if it can predict well on the test set. But yeah, so we could also run it on a few others. Like if we want to do this next prompt, which the target is 4, it was the 4th model. Run this through. It does, in fact, predict 4 as the target. So a little bit technical there at the end with showing you all how the code works to run these models, but I hope that was helpful and you learned something new here. Yeah, I see there's been a good number of questions coming through. Unfortunately, we won't be able to get to all of those, but do send us a message and we'll try to answer or at least respond to them. If they're not anonymous, we'll try to respond to as many of them as we can. I hope you learned something new and that you appreciated this. And thanks so much, Morgan, for having me.
Yeah, thank you, Rob. Thanks for an amazing session. As I said earlier, we will be sending out a recording of the webinar later this afternoon. You'll get it via email, so please be on the lookout for that. And if you have any questions, please let us know. Thank you so much, and we hope to see you again soon.
Thanks a lot. Bye, everyone.